Welcome to this second video on BF.NET. Last time we wrote a simple interpreter for the language, and this time we're just going to extend it slightly and improve on it in a couple of places. So since last time I've uploaded the code into GitHub, into my repo up here, David Betteridge /BF.NET, and I'll put the link to it in the video as well. And we just returned it. And this is where we got to last time, is we wrote a simple interpreter where it asked you to enter your instructions, and then we went through, passed the instructions one by one and executed them. So there's a couple of areas we can improve on. First of all, these loops here are a bit nasty when we're trying to find the matching close bracket for a particular opening bracket. We could do all this once and then just look up the location of the closing bracket as we need it. And the other thing is this infinitely long tape. At the moment we fixed it to be an array of just 10,000 bytes, but the problem is, in theory, you could extend that. You could overrun that and overflow. So I think we will fix the tape problem first. And the way we're going to do this is we're going to abstract this array out of here and into its own class. So we'll create a class which we can just call tape. So we've moved that in there. And our tape's going to have two operations. It's going to have the ability to read a byte from a given memory location or address, and it needs to have the ability to write a byte to it as well. So when you're writing the byte, you take the address and the byte we're going to write. Right, doesn't need to return anything. So. And the implementation for this is fairly straightforward. So for reading, we can just return whatever's at that address. And likewise for writing, we can just populate that address. So that's a pretty simple implementation of our tape. And then we just change the code down here to actually use our class instead of the array. So these bits here we need to change. So here I'm going to write, and we're going to write to there. And the thing we're going to write is its current value plus 1. And as before, we need to cast our integer back to a byte again. And we need to do the same thing when we're decrementing values. And also when we display them, instead of reading them from our array, we now read them from our tape. And finally, when we've pressed a character, we need to write it back to the tape. And then down here, where we're checking to see whether it's 0 or not, we now use our read command. Okay, and we just take our sample input and run it, and just make sure our program's still working. Yes, that's still working nicely. Oh well. So the thing is, all we've done is we've just abstracted our array out there into our class. And this is sort of our simplest implementation we could have as a tape. Now, obviously there's a bit of a problem in that if we started off with, if we set our data point to be 0, where we look at to begin with for a tape, and we set our array size to be really small, like 2 for example, And now when we run our program, it's going to fail because we're trying to access elements which are beyond the length of that tape. And we don't know how long we want the tape to be in advance. So we're going to need to do something different to this. So there's a few different approaches we could take. And the way I'm going to have is just all I'm going to do is as soon as we get off the end of the tape, I'm going to double it in size. But one of the things we've got to be aware of is, if you imagine this is our tape, and we might start there, that's our initial pointer, so our pointer's there, and obviously we can keep moving to the right, and if we get to the end of the tape, we can then double it in length. So when we get to there, we just double its size and so on. But equally, we can also go to the left, because we can decrement the pointer, and so as soon as we go left one position, we're actually going to have the same problem. So I think the way I want to solve that is instead of having just one array, I want to have two arrays. One for all addresses which are greater than 0, and a second one for all addresses which are less than 0. So I'll call them, well, I guess negative, positive. And so now we just need to do a bit of maths to make sure we're accessing the correct element. So reading is, well, okay, so the rule is if the address is greater than 0, then we're going to read it from the positive array. And if the, in fact, greater than or equal to 0, positive array. And if it's negative, we can read it from the negative array, but we need to make the address positive. However, we want to map, so the address -1 is going to get mapped to 0, and the address -2 will get mapped to -1, so we have to add 1 there as well. And then we have to do the same thing when we're writing the values. It's exactly the same, but instead of reading, we're going to write. Okay, and then, so we haven't actually fixed the problem at the moment because our array is still 2, so we can still get the problem where we can try to access something that's beyond the size of the array. So we now need to check for that as well. I think we'll add some braces in around this. Okay, so when we read a value, so if we say, if the address we're reading is greater than or equal to the length of our array, then we've shot off the end of the array. We've gone too far. But we know that we haven't declared any values for that yet, so we couldn't have written to it yet, so its value must be 0 at this point. And we can do the same thing with negative addresses as well. Call it index. And then likewise with the writing, so this is where it gets a bit more interesting. So we'll add our braces in again. So this time, if we've gone off the end of the array, we don't want to return 0. Instead, we actually want to make the array bigger, so we can actually write the value into it. And the way we can do that is we can use array.resize, which takes in the array we want to resize, which is that, and its new size, so we're going to double it in size each time. by ref. This doesn't completely solve the problem, however, because if we had the case where we had a really short array, say 4 values, and we could advance several places to here, and then we could write a value, in which case doubling the array would actually be enough. So for example, if the array was at size 4, but then we moved 5 places and then tried to write a value, even doubling the array wouldn't be long enough. So we can solve that easily enough by, instead of doing an if statement, we can make that while loop. So we keep going until the address is in the size, is within the bounds of our array, and if it isn't within the bounds, we just double the length. So it would go 2, 4, 8, so on. And then we can do the same thing with our negative values. And then we can just put a bit of code in to print out the size of our array to make sure this is working. So if we go lots of places, so size of the 4, that wasn't enough, 8, and then had to do it again to get to 16. And if we go this the other direction, we've broken it. So the address is looking. Oh, because wants to be index, not address. So if we go that way a lot of places, and we'll put a plus in there. It looks like it's worked, but we forgot to actually print it out. Okay, so that's working, and that's now resizing our array automatically. Okay, so this is one implementation of our infinite tape where we just keep doubling it in size every time we run out of space. There's obviously other ways you could implement it, and some more optional, optimal as well, because doubling the array in size each time is quite a slow operation. The next one we're going to look at is these loops here, because every time we do a loop we have to then look forward to find the matching close bracket. Because our code can never modify the program because our language doesn't support it, we can just work this out once and then remember it. So what we can do is have a dictionary where we can store the index of an opening bracket and the index of its corresponding closed bracket. And we can also have a second dictionary which goes the other way. So from any closed bracket we can find the location of the opening bracket. So what we have to do is we have to do a parse of the instructions first to populate these dictionaries, and then we can just consume them. So the parse will be so the instructions on length. So that's our current instruction. We'll do a switch statement. And if it's an open one, so rather than have to keep looping forward and then looping back again and forward again, what we can do is we can use a stack to keep track of the open brackets as we find them. So that will be a stack of integers. So just include that. So whenever we find an open bracket, we just remember the fact we just found an open bracket. So we just push that onto our stack, and we remember its index. And then whenever we find a closing bracket, we know it must match up with the one that's currently on the top of the stack. So now we have our dictionary, which will be, so we have two dictionaries, one which is given an open bracket, we can find our closed bracket. And then we also want a dictionary that goes in the other direction. So given a closed bracket gives us the location of an open bracket. So our closed location is our current index, and our open location is whatever's on the top of the stack at the moment. So obviously, if we've got a mismatch of open and closed brackets at this point, then we're going to get an error message, but we can look at that in a moment. So then once we've got both of those, we can then add them into our dictionary. So that's just going to be, oh, I don't know. So that's going to go from our open location to our closed location, and then we'll do that the other way as well. So that builds up our two dictionaries, and then down here we can then start to consume these. So whenever we find an open one, and now we know we need to jump to its corresponding closed location. So that's going to be that's the open bracket location. So that's going to return its closing one. So we can just set that. Okay, it's as simple as that. And then we do the same thing when we have to jump back the other way. Only now it has to be close to open. And we can try it with our test program. So, I'll tell you what's been annoying me is that it says okay, so that's still working because it's obviously done the loops properly to give the right answer. So what else can we do? We can do we can have a so that passes fine, but if we've got an unmatched number of brackets, then we've got an error. So I think we need to fix that. So that at the moment is failing at runtime, but we can actually determine this is going to fail even before that. We can determine it at this point up here, which will be a better place. So there's one case which is where we've got more closed brackets than open brackets, in which case this pop will fail. So that's reasonably straightforward to check for. We can just say if that count for 0, it means we've got no matching open brackets at all. And we can throw in new exception. So that's if we've got more closed brackets than open brackets. Let's try that. Okay, that works. Bracket at position 2 is no matching open bracket. And the other case is if we've got more open brackets than closing brackets. So we can track that because we know when we get to the end of the program we've still got something left on our stack. So it's the opposite to this. We could actually have more than one on the stack left over, but I guess we just report the first one. And in fact, it might be better if we maybe we're better off to write that to the console instead. And then break out the loop. And we can display errors in red. Use the colours afterwards. And then we can do something similar down here. And I think we just do something quick and dirty, which is code equals true. So once we hit a problem like that, we record the fact we've got a problem. So code equals false. And like down here. And then if we're here, we'll just continue out the loop, and we won't actually bother running the program. So we read in the instruction, we try and match up the brackets. If we can't do that, report it to the screen, set this flag to false. If we get to here and the flag's false, then we just jump out and ask the user for their next command. Just make sure that works. Okay, so this case, that works. That works. Turn the open brackets. It's fine, and turn the closing brackets. Oh yeah, that's fair. That's better than I was thinking. Okay, so in this video, we've addressed those two issues. We've made the tape infinitely long, or at least the ability it can grow when it runs out of space. And we've also made our code for looping backwards and forwards a lot more efficient. And we've also done some parsing to actually make sure the program's got a reasonable structure. There's obviously other ways we can optimize the code as well. Like all these pluses here, for example, we could just do a plus. It'd be a lot more optimal just to say +8 rather than 8 lots of +1. But this language at the moment doesn't really lend itself to doing that. We don't have that representation yet, and that's something we can look at in a future episode. The other thing to point out is this code is nowhere near as efficient as the original code, but because we've now got a lot more comparisons going on, whilst before we were just reading and writing from a simpler way. So next time we'll look at actually generating some C# code rather than running it as an interpreter.